بسم الله الرحمن الرحیم ولا حول ولا قوة الا بالله العلی العظیم حسبنا الله و نعم الوکیل نعم المولى و نعم النصير. Thank you for joining us for this session. I will give a very quick review of last session, and then we'll continue on some examples and hopefully a very attractive new method of successive screw for forward kinematic analysis of a serial manipulator. What we talked last time was that regarding the most general form of a link, we can assign some frame to it. We call it the Denavit-Hartenberg convention with Paul convention. And then we have some parameters, 4 parameters that can be extracted from the Denavit-Hartenberg frame assignment. And by doing that, we can find a general transformation from one frame to another frame, considering that this link has all these 4 parameters available. Of course, in many examples, some of these parameters are simple, either 0 or 90 degrees or something like that. And this matrix will be much simpler than general form. But in any case, if we have a link that has twist, has offset, has some angles, then we can have this transformation and then find this transformation from one joint to the other. Having this homogeneous transformation found for a robotic manipulator, the main important issue in terms of forward kinematics is to find the loop closure or to matrix form of loop closure. As you see in here, we can have a loop closure method. I have written it in this way. Let me go to the Paul convention. When we have a manipulator, for example, with 3 link or 4 or 5 or 6, we design the loop closure in this way, exactly as before. We have the blue and red vectors. We have a blue and red matrices. The blue matrix is the end effector position and orientation with respect to the frame, that we can write it as a homogeneous transformation, simply as T3 to 0, for example, in this case. And then having the red vectors was the consecutive transformation that we can get by the joint angles and joint parameters. And these are written by these 3 transformation here. So we manipulate, we have found this by the Denavit-Hartenberg convention. We simply multiply this all together. We have an equation in terms of joint variables, Q, and this one we have an equation in terms of task manipulator, script X or Chi we call it. Then we can relate these 2 together in terms of a matrix form. And in a matrix form, as you see, for example, in this example, the non-zero element will give you the forward kinematic case. And as you see here, usually we have 3 position vector making equivalent to the position vectors here. Here we have only 2 equations, and we have an orientation matrix, which is a 9 parameter valued matrix that can be represented as 3 independent equations. And if we write, in this case, we have only 1, since it is a planar case, and then we have 3 equations like what we have in here. So we can manipulate that and use that. The most important thing is to find the Denavit-Hartenberg parameters, and as I mentioned, finding them is not unique. because of some freedom of choice that we have in frame assignment. So you might have different parameters in terms of the manipulator representation, but final solution, final kinematic problem is usually the same. So if we go, we have this example and also the SCARA manipulator example, a 4-degree of freedom. As you see, I will try to emphasize on the joint variable and task variable, because this is the main important issue that we would like to continue on kinematic analysis. Then we can, we have also given 3 PP manipulator. The base of a manipulator, it is a cylindrical robot which has a R and 2 P manipulator. This was also given in the last session example. And usually a general manipulator has 6 degrees of freedom, 3 degrees of freedom for position, as we talked before, and 3 degrees of freedom for orientation. Usually we have a base. This base could be cylindrical, it could be 3RR, or it could be many different approaches, usually with three parameters as we have here. And we have a wrist. The wrist, like our wrist, is a special design, joint orientation or kinematic design that is in many cases is very simple, as we call it a spherical wrist. A spherical wrist means that we have a ball and socket. We have a wrist that can rotate in 3 different directions, but as we discussed in our kinematic relation, we usually write it down in terms of primary joints because they should be actuated. So we have, as you see here, we can have 3 actuators here. One actuator, as we call it, in Z-axis. As you see in this direction, we have the Z-axis here, and then we have a perpendicular axis to it. We have another rotation we call theta 4. We start with theta 4 because usually the wrist is on top of the arm. So we have 3 angles for the arm, as we had in the previous slide, and 3 angles for just the wrist, 4, 5, and 6. We have an angle theta 4 about this Z-axis, a perpendicular joint. We have an angle of rotation, as you see, in this direction, which X, Y, Z, if we call it, it is in Y direction, in base frame Y direction, but we call it a Z4. And then we have another actuator, again perpendicular to them, in this direction, which is again, as we see, in Z5 direction. And usually all of these 3 angles are intersecting at one single point, which is the wrist point. We call it W usually, this point. This is a point of interest. And these 3 are usually perpendicular. And we have a hand, a base, or a gripper with a length D6, as you see here. That we put another frame here in terms of our end effector point. We call it Q point, or the end effector point. So as you will see here, in terms of different approaches that we can use in here, let's find the Navitt-Hartenberg parameter, the frame assignment. As I mentioned, the Z-axis are always the axis of rotation. So we have an axis of rotation. In this particular case, we call it Z3. One here in this direction, call it Z4, and one in this direction, call it Z5. All of them intersecting at the point, and then we can find the x-axis. The x-axis was the common normal of these 2, but since they are intersecting, it is simply any perpendicular direction that you can use in this plane. And as we see, Z3 and Z4 we call X4 in this direction and X5 in this direction, perpendicular to Z5. And finally, the Z6, the final frame, we use very similar to Z5. As we see, we have X5 and Z5 in these two directions, the same direction as X5 and Z5, but with the offset length of the gripper or the end effector. Of course, as I mentioned, these are not unique. You can have some freedom of choice here to select some particular cases. Of course, not the z-axis. The z-axis are all assigned by the direction of rotation that we have in here. But the x-axis could be, instead of being this way, could be in the other way. But if assigned in this way, if we consider it this way, then we can find the Navier-Hartenberg parameter. Let me go a bit slower in here as another example to find the parameters. Since we have a spherical wrist 3RR manipulator, our joint variables or are the varying parameters that are within the Navier-Hartenberg. We call it the joint angles or joint variables are theta 4, 5, and 6, the angles that these three actuators can get. But in terms of offset, we don't have any link length because all the lengths are intersecting on each other. This is a special manipulator. It is a wrist manipulator, so we don't have any link length here since we have intersecting. But the angles are always, 90 degrees. But why minus 90 degree, as you see here? If you look at the Z3 to Z4 and you find the angle from Z3 at this, let me show you here, with the right hand rotation. If you rotate Z3 to Z4, this angle is 90 degree, but it's not in the direction of X4. It is in the minus direction of X4. So it is minus 90 degree. Of course, you can, this Z4 was somehow arbitrary. You can use it in the other direction, and if you use it in the other direction, this minus pi over 2 will become plus pi over 2. So this is minus 90 degree from Z3 to Z4, and then from Z4 to Z5 we have again a 90 degree, but as you see, this 90 degree, if you put it there this way, is along or about X5, so it is plus 90 degree here. So simply by these two 90 degrees, we have a spherical RRR wrist manipulator that can be considered quite easily. And the D6 form is the offset that we have for the end effector point. All the other parameters are 0, and then we can find quite easily the transformation matrices. Just use simple formulation, that the substitution in the general formulation. As you see, it is quite simple. Since we have only 1 degree of freedom here, we have minus 1, and this is because of minus pi over 2 degrees of rotation in alpha I angle. And we don't have any DI, as you see, DI or AI, no length. So here is 0, 0, and only the last one has D6. Then we write the loop closure, and in terms of the loop closure, we don't have much of precision here. We have 3 orientation angles, as we call it here. The wrist will give you the orientation that we can pick a object by the manipulator, and we have these 3 angles, so we can write TE to 3, actually the base frame. We can find it in terms of the task manipulator. We have a rotation matrix or orientation considered by 3 angles. This could be any type of angle that you wish. We prefer to use the screw axis, the axis of rotation, and the angle of rotation about this axis. And we have a offset D, as we have D6 here, which gives you the length of the manipulator here. And by multiplying these 3 homogeneous transformation we find in this part, we will see that we have a rotation matrix which is quite full in terms of these 4 parameters. Theta 4, theta 5, and theta 6 are written in here. And also the position comes in here. Only one last remark here. If you look at the rotation matrix here, about more carefully, does it has any, does it remind you to any representation we have before? Anybody could contribute?
Polar angles.
Which polar angles? We have 24 different type of Euler angles. And if you see here, we have X, Y, and Z. Since we have 3 rotations here, the first one is about Z, the other one is about Y, but minus Y in this case. And the other one is about X. If you look at the Euler angles, this shows you a Z or Y X Euler angle as we had it before, but one of them is minus, and that's why, because we have here a minus sign. It is very similar to the Euler angle that we use. And this is the why Euler angles are so useful and can be used as a good representation. Of course, I don't recommend them, but they are very useful and has been used a lot because usually in mechanical design, we have some sort of perpendicular axis of rotation in the wrist, as we say in here. Of course, you could have other arrangement. Instead of having the second degree of freedom here, it was quite possible that we rotated 90 degrees and have it in the other direction. Then we have another Euler angle representation. And this will change the rotation matrix as we see. For forward kinematics, we don't really care about that. What we have is, we have a one-to-one correspondence between 3 angles here and 3 angles here. If you use these 3 angles as the right Euler angles, you can easily find phi, theta, psi from that. But if you use another form of Euler angle, then these relations are not very simple to be found in terms of inverse kinematic. Of course, if the theta 4, 5, 6 or the Q parameters, the joint variable parameters are given, you can easily find that, and you can easily equate this and find the rotation matrix, the orientation of the end effector in terms of matrix representation. But assigning a right Euler angle will help us a lot in the inverse problem that we will talk about it in the next 2 other sessions that we have. Anyways, these are simple manipulators, only 3 or 4 degrees of freedom, but usually our robotic manipulators are 5 or 6 or even 7 degrees of freedom. We will talk about different approaches here. Here I have brought for you 2 other manipulator. One is 5 degrees of freedom, which is all rotational 5R manipulator, theta 1 to theta 4. As you see, we have a base, a rotation about the base, two links that gives us outreach, and then we have a wrist here. The wrist is not a full wrist with 3 degrees of freedom. It has only 2 degrees of freedom, and that's why we have 5 degrees of freedom as we approach here. And the last example that I will provide for you in this class is the 6th degree of freedom, which is the most general form of manipulator, fully actuated manipulator that we can use in industries. Again, here we can assign the frames in about the axis of rotation. Here we have used in this one. In this example, we use the Z to be inward into the plane. It could be outward as well. This is your choice, but in this example, as you see, X, Y, Z is inward in the plane, and the same here and the same here, and then we have another rotation as we see in here with Z4, and finally the Z5. The final point is put on the end effector point on the Q point, very similar to Z4 and Z5. And then we can find the X values regarding the offset that we have in this manipulator, which is quite similar to many industrial manipulator. The second link has, or the second joint, we have a first joint which is rotation out of the plane. Usually this is the case. The base is vertical, and we have rotation about the base. But this one, as you see, has a link length. It has a difference in this direction and also difference in this direction, D1 and A1. And since D1 is along Z and A1 is along X, we can see that these A1 and D1 comes into the picture of the first case. And the angles that we have, if we have Z1, Z0 here and Z1 inward into the plane, then we have basically minus 90 degree, as you see in here. Again, if you don't use inward and have an outward Z, then this angle would be plus pi over 2, and it doesn't really change that much the representation that we have. And then again, the other one are very simple, like 2R manipulator. We have theta 2, A2, theta 3, A3, and here we have another angle which we can see, Z4 with respect to Z3, which is inward into the plane. Again, if we go Z4 to Z3, Z3 to Z4, it is along minus X4 direction. So again, we have a minus 90 degree here, and the parameters are finalized with the last end effector point that we have, D5. So we have 5 degrees of freedom here. The task manipulator is not complete. It is only 5. 3 of them is the position of the end effector, and 2 of them gives partial orientation of the end effector. And in many applications, we don't need rotation about the axis of rotation. So consider that you are doing drilling or something, so you don't need to have rotation about the last axis, and 5 degrees of freedom is sufficient for many applications that we have shown in the first session of the class. We have the parameters, then the rest is quite simple and arithmetic. You can use symbolic manipulator of MATLAB, as we will provide for you the examples of them to find all these transformation matrices, and then the final transformation matrix, and then having the loop closure matrix equation here, equate them to each other after manipulating these manipulations. You can find it this way: UVW, 3 vectors of rotation matrix, and then a Q, which is a position vector, and we have given all this direction here. As you see, it is much more sophisticated, and theta 1, 2, 3, 5 is in the U direction, 1, 2, 3, 4, and 5 in V direction, and in W direction we have 1, 2, 3, and 4. So the fifth direction will basically change the V in the rotation. And the Q value is also component-wise, depending on all the offset and the length and the twist, the angles that we have in here. As you see, we have A1, A2, D5, and all the angles going to. This gives us the forward kinematic. If Q is given, theta 1 to theta 5 is given, then we have the position and orientation. As we see in here, a general form of position and orientation, all the components are quite easily found. The inverse problem is not that easy. We will talk about that later. And the last example that we use is a Stanford manipulator. It is a research-based manipulator designed in Stanford University. And in this manipulator, this is a bit different from usual 6 degree of freedom manipulators we use in robotic manipulator. We keep it for your project and for your further development that you would like to know. Here we have basically one prismatic joint. All the others are, as you see, 2 are P and 3 R. We have 5 rotary joint, again a base which is out of plane, then axis here which gives you the rotation about this axis, but in here we have a prismatic joint, and we have a translational motion, and then we have a wrist here, theta 4, theta 5, and theta 6 as before. And as you see, it is also a ZYZ, the direction in the in terms of Euler angle. We have 3 perpendicular axes of rotation in our wrist orientation. And here then we have the full 6 degree of freedom task variable, 3 degree of freedom XE. If we have the end effector putting in at the end of the point that we have in here, we have some length and some D parameters, as you see, quite easy. And as you see, the red one, we have the 6 variables that we use it in our Q variable. Again, we do the frame assignment quite easily now. I guess you have been quite familiar how to get the Z1. It is quite easy, and the direction between these two, we have a number of 90-degree rotations here, and then by these offset variables are here. In this manipulator, the AI is interestingly, all AIs are 0, and we have only DIs because the length of the length are, since they are perpendicular to each other, are not along the x-axis. They are usually along the z-axis, as you see D2 here and D4 here. Again, another point that you should consider, x0 is considered at this point, not at the base point, and this makes it much easier to follow the kinematic problem. If you use the Craig convention, then usually we start from this point and we have this length coming into the practice. But usually this length is simple, and the base of the manipulations fork space can be considered from this point. Anyways, if you have this, again, we have a wrist. We have worked for the wrist, the spherical wrist before. We have a RRP manipulator. It is different from the examples that we have. We can find the rotation matrices and the transformations here. And then doing some manipulation with, of course, symbolic manipulation of MATLAB, you can multiply this together and find the final form that, as you see, it is quite complicated. It is a number of sine and cosine of different variables coming into the picture again. All the variables are being used in here. Okay, very good. We have half an hour spent on this example. I would rather just leave it to you to read from, but since the last session, I thought that you prefer to have more example. It is really overwhelming. This number of examples are never given in any book. Only one or two is given, and then the rest is put for you. But we have used different books here to give you more example here. If there is any questions or anything that's not clear, please stop me here and ask your questions.
I have two questions.
Sure.
One of them is about the offset. I just was thinking, is there any design advantage in each of them, or just it depends on the application, that some of them, the rotary joint is just at the end of the link, sometimes it has some offset?
What do you mean about advantage? Let me first ask you, what do you think would be an advantage?
I don't know, maybe work distance.
No, actually, this is usually because of the design constraint. When we are putting mechanical parts on top of each other, usually the motors should be placed in a position, and it is quite hard mechanically to put everything aligned each other with no offset. It could be also not very beautiful in terms of looking at it. I don't see any advantage, any particular, at least I can't recall. Maybe there is a particular application some advantage, but usually this is the way the mechanical design or the arrangement of the links and joint will dictate to us how to proceed the number of them. What I would like to say is you have the power of including all sophisticated joints and links here. But this doesn't mean that it is good in the design. I think, as you see, and the evolution of the robotic manipulator, for example, the first robotic manipulator used for 6-degree of freedom was Puma. Puma is very, very, let's say, I can say ancient or somehow historic. Right now, there is no Puma in any industry. Of course, there are in some research lab from all. In Puma, you see a lot of offsets. But as the designs comes better and better and better, right now the robotic manipulator, since we have the 3D printing and we can have some sort of better design in terms of the shape, usually these offsets are becoming less and less. I think it is much better not to have any offset. In terms of kinematic analysis, of course, it is much simpler if we don't have D or A's, or the twist angle, because we have this one. But I saw another advantage. I cannot talk about it right now, because as I mentioned to you, first we should define what is an advantage. Then we can say that, how we can design a manipulator to have an advantage. Mathematically speaking, having an advantage means we have a measure of goodness, a measure of being well designed. Up to now, I haven't discussed anything about that, but I can give it to you some very good examples that comes from the nature, design of God. All of them are very good. And if you look into them, you see that there is something optimized there. When we have a measure, then we have an optimization, and then we can discuss it. It is too early right now. Just bear with me. In the fourth session, in the next chapter, I will give a lot of very, very interesting points that can be considered as a measure of goodness or as a measure of advantage, and then we can discuss about that. Is there any other questions?
Actually, I have another question.
Sure.
How we can model a spherical joint? Because it has 3 degrees of freedom, but the angles are not actually separate from each other.
I didn't get your question. Your voice was, what is the
I'm saying how we can find the kinematic analysis if we have a spherical joint. Because we have 3 angles, but they are not actually separate from each other. So,
do we have any spherical joint in any serial manipulator?
we might have.
Do we have any in practice?
Maybe not in practice.
Not in practice, so I don't answer it as something which is just imaginary. We have spherical joint a lot in parallel manipulators, and there is a reason for that. If you find the reason, this is much better to find. We are talking about some engineering concept, not mathematical concept. We don't have spherical joint in a serial manipulator. I don't say we don't have it. It is not possible to do. No, it is possible, but we don't have it because, as I mentioned, we have the joints, as you see here, we have a joint angle here, and each of these joint angles are actuated. We would like to control them. And designing a 3 degree of freedom actuator, a spherical actuator, is almost impossible for human being. It is quite easy for God, like this, and you see it in nature. It says kun fayakun, he wants and it will be done. But for us, it is almost impossible. We can have 2 degree of freedom. We have designed something like that. I don't say it is impossible. It means that it is never possible. At least up to technology that we have to here, it is very, very difficult. So we don't have a spherical joint not because it is not possible to design the mechanical design. No, the actuation part is very difficult. And that's the axis of rotation. We are very familiar and easy to work with actuator that has 1 degree of freedom. We have a motor. The motor will rotate along an axis. But a 2 degree motor, 2 degrees of the motor actuation, you think it is a bit much more expensive and difficult to do. It is possible to do 2 degrees, which we call it a unitary actuator. And I mentioned to you a lot, our eyes has a 2 degrees of motion. You look at my eyes in this direction and up and down, left and right. A spherical joint is basically moving 2 degrees of freedom with some muscles, 2 types of muscles that been used in the eye. But usually, if you would like to design artificial eye, we should separate these 2 degrees of angle, like a gyroscopic effect that we have in this. So we don't have it in practice, and therefore we don't consider this here. But in parallel manipulator, we have a lot of joints. We have a lot of difficulties there. I will refer you to the parallel robotic course or the book there.
Thank you.
Thank you for the very good questions, but is there any other question?
Yes, may I ask one?
Sure, please also introduce yourself.
I'm Mahdi.
Mahdi Mohammed Mahdi, yeah?
Yes.
Perfect.
In a Stanford manipulator, exactly this slide, will you explain more about the third joint, X3, I mean, when Z2 and Z3 are coaxial, is it arbitrary to choose the X3 everywhere?
Okay, very good question. Thank you. Actually, why this? First, the question is why Z2 and Z3 are coaxial and how we can use the X1. Here is the degree of freedom, the freedom of choice that you have. You can find any X that you want because these two these two axes are coaxial. They are on top of each other, not intersecting, not parallel, and not in different space. They are exactly on top of each other. Why this is happening? The reason for that is because we have a prismatic joint and a rotary joint on top of that. If we have rotary joints, it was nonsense and not useful to have two rotary joints on the same axis because they will be redundant. I can't say nonsense, but it is not usual to do that. But here, since we have a prismatic joint and a rotary joint, it is possible to do that. The reason why we used X in this direction, there is no reason for that. We should have a perpendicular to this. This could be, with 15 degrees of the rotation. But we use it usually simple. And the most simplest one, since it should be basically perpendicular to that, we use, the axis which is 90 degrees or 0 degrees to the other axis. And here we use this direction. But you can have freedom of choice, and it will be changing nothing, Why? Because, you have this one, then you have the other ones on top of them. So if you give an angle here, the angle will be reduced there. This will be changing. This will be changing too as well. But the final version that you get, which gives you the orientation and rotation, doesn't really matter to your selection of the axis. Thank you. Very good question. Hossein has also a question. This is the last question. I would like to spend some time about the successive screw.
Good morning.
Good morning.
Excuse me. In slide 24.
Yes.
Yes, we had A2 in this table.
Yes.
We have
it.
Eternal A2.
Yes. What is A2?
What is A2?
Hossein, you tell me what is A2. Why you ask me? Just ask yourself. What is A2?
A2 is the distance between Z2 and Z1.
Okay, in direction of?
Common perpendicular, in direction of X2.
X2. So look at here. We have, as you said, we have an offset here. You see here, I didn't put it in here, but
yes.
If you see, we have an offset between Z1 and Z2, and this would be the direction that we have in terms of, of course, if you look at the book, I just take a part of it, and as you see, I have added here some part, to show you this is D6, for example. But usually in the kinematic one, it is not given that.
My question is, I didn't see the book, but we have intersection between Z1 and Z2. Is there any...
we have Z1 here and Z2 here. Perfect. Now I understood what is your question.
They intersect,
we have D3, D2 and A2. D2, yeah. Yeah, now I can understand what is going on. We should look at not the kinematic here, just look at the true picture of the robot. Let me give it to you in this case, as you see in here. You see here, it is like this. We have a prismatic joint. This prismatic joint is, we have elongation and reduction in size, as you see in here, D3, and we have a fixed part. Here it's D4, but for that one is a fixed part, which is A2 for the system. Both of them gives you the length. Yeah, that's also a very good question. Thank you for look at the physical meaning of that, a physical picture of the robot. You can find it. Thank you. Okay, I will go to another approach, which is much simpler than this approach. As it is unbelievable simpler, and it becomes from an idea. Of course, it is not quite well known. It is not given in many books, and I don't know why. Because it is based on screw. I would like to spend at least half an hour talking about that. The screw displacement, as we discussed before, we had, given that the basic intonation in the last chapter, but this screw representation has some physical meaning. You know that if we have a rotation along an axis, so that this axis would be the screw axis. And as we see, screw has two things. Not only this, because of the Schall theorem. You remember the Schall theorem, that if we have an axis of rotation, then we can have the translation along this angle to be considered as the translation motion for a general motion. So the screw axis is very, very useful. You can find some books on screw theory, نظریه پیچه ها, we call it in Farsi, پیچه, screw, and نظریه پیچه ها, the screw theory, and screw theory or screw arithmetic in kinematics. We have two books about that. I don't want to go through all the details, but if someone is really want to work on mathematical concepts of that, it is good to use that. The importance of a screw is it is somehow inherent with the motion of the system, and it makes the mathematics that we are using quite simpler. So we are doing another approach completely different from the Navitt-Hartenberg approach. Just forget about the Navitt-Hartenberg now. But much simpler. I don't say that, much simpler. I mean, 100 times simpler. Of course, a few times simpler, with some more intuition in terms of physical concept. And also, as you see, the problem that Muhammad Mahdi and the other people talked here, we don't have, a different representation here. The representations becomes much more unique and understandable. Of course, there are some freedom there too, but much better. So, if I were at your age, and I have the freedom of choice to use the Navitt-Hartenberg or screw, and I have my experience after 30 years of experience in robotics, I would definitely use screw. But since this is not very well developed in many textbooks, it is somehow mahjur. This is somehow not well received in the practice. But let me explain to you, and hopefully I will write a book myself on this topic, and then it will become much more visible for robotic community. I'm going through the Tesai book, And also the new version of Niku book, Iranian guy in United States, also the second version of that has been representing or reproducing it in his book as well. So what we say, let me just remind you something about the screw, as I mentioned. As you see in here, the method we are using is successive screw. So we have a number of screw, and this is representing the loop closure method. Instead of having a loop closure in terms of the matrix form or in terms of vector form, we have a loop closure in terms of screws, successive screw. We call it not loop closure here, we call it successive screw. What is a screw? If we have a rotational axis, we know that there is an angle about it. So this could be represented by a screw, not a z-axis. In Denavit-Hartenberg, we call it a z-axis, but here we call it a screw. And this is a screw. When we have a screw, you remember that we should have a S0, a difference, an offset, the D parameter, the translational part as well. The translational part also is given here. How far it is from the other one, S2, how far it is from S1, and how far they are from the base frame, as we see here. So we have a base frame. We don't consider, number of frames here and frame assignment, which is a hassle, basically, in my opinion. I don't want to go that directly to that. You should learn both methods, don't forget about it. You should learn both methods, the method of Denavit-Hartenberg and the method of screw. But here it is much simpler since we need only 2 frames. One frame is the base frame. Whenever you want to choose it, of course, we usually put it on the base, and one frame it is on the end effector. Maybe on the end effector, if you are looking on the final point of the robot, and in many cases we put it on the wrist, usually to make the much more simpler, the end effector. Instead of having at the end point, maybe we put it on the wrist. So it is your choice, either P or Q, we call it, as you see here, P or Q, it is the point of interest that you would like to close the kinematic loop here. And then what we do, we use the displacement. Any rotational angle has a screw axis. Any prismatic joint also has a screw axis. The screw is the translation. The rotation is a screw with a rotational angle. So in rotation axis, the screw is about the rotation axis. Exactly the Z components that we have in the Denavit-Hartenberg, we call it the S hat or the dollar sign. The dollar sign is the screw axis here. And also we need the displacement. So if we have a screw here, we have it how far it is from a base frame. We can find it from a base frame. And then we can have a successive screw. We have a number of these coming here. If we have designed a screw, if we have found a screw, we can have the homogeneous transformation as well. Instead of going through the homogeneous transformation I showed you at the first slide of this session, which was the Denavit-Hartenberg, we can have another transformation very similar to that, not exactly the same, but it has some parameters. The parameters come with the screw. I will give it in the next screw. And then we apply the loop closure in terms of the screw. And this is much simpler. We call it the loop closure is that in terms of matrix, the homogeneous form. I call it A here just to make a difference between what we have before and here. This is exactly the homogeneous transformation we get for the end effector, but with screw representation. And this is the screw representation of each angle, each joint that can be found together. And we have a successive one, A1, A2, A3. As you see, we go from A1, A2, A3 to the effector, and we find the loop closure. So in here, we have the similar thing. Should multiply here, make it equal to this one, but this is don't need to have 100 number of assignment for it and so on, and we can use it that way. How we can do, just remind you the screw representation. You see that I intentionally put it AI here instead of T. This is the same thing. This is the similarity, the homogeneous transformation, but we call it the screw displacement. This is 264 from my book. We gave it in the last session, and hopefully today I will provide you with the first assignment. On the first assignment, you will work a bit on these parameters. Be ready to get the assignment. I was very busy these days. I couldn't put it on the web. I should check that your assignment and then finally make it a bit simpler for you and to have it hopefully today after the class. So we have this rotation. You remember we have a S hat and theta, we have a 0 and D, we have these two, we have actually 8 parameters with 2 constraints. It is only 6 parameters. The parameters are given here, not in terms of Euler angle, but in terms of so basically we can find the S1, S and theta, this part is filled, and if we have S0 and D, this part, Px, Py, P0 is filled. Having this in mind, we can define it quite easily. I will give it a recipe to you, which is very, very effective. What it says that it doesn't matter how you put the screws to each other. This is the basic point. And usually we make it in this way. We make a home position. We call it consider the reference in the manipulator in reference position. We put it in the most simplest form that we can get the manipulator. Instead of having it this way, we make it very, very easy, like a manipulator which is along this way. Very simple, in a position that we can find everything quite easy. And then we find the screw axis. So instead of having theta arbitrary angle, usually we make all the angles equal to 0 to have this representation done. We call it at the reference position. With this position, we can find the screw axis and we can find the difference A1 to AIs as well. Then we have a target position. A target position is having a non-arbitrary one, something quite complicated in space, but since we don't use the internal one, we are just using the final end effector position, we give a most general form of the end effector that we can have there. And then we find XE and also the orientation, depending if it is planar or it is rotational. As we see, 6 degree of freedom, 4 degree of freedom, 5 degree of freedom. Find exactly like before, the target position is this TE with respect to 0, we call it here. And the target position, we call it with RE and variable X, the position and the orientation of the end effector. And then we just simply use this kinematic loop closure, which AE, we find it from here, is equal to the number of multiplication that we find it in here. This part is quite similar to that previous one. We have some manipulation here. What is much simpler? This is exactly like before. This is almost like before what we have done. The most interesting part is this part. We don't need to find the screws in a very difficult way. We find it in very, very simplest way. The XE0 and RE0. I will give it some example to you to understanding. So we put it in a reference point, we find the screws, and then we just multiply everything together. Do we need any z-axis? No. Any Denavit-Hartenberg parameters? No. Any DAI? All of them are here given in terms of the screw, the S-axis and S0 axis that we have in here. Let's go by some examples. About 15 minutes about the method. So simple. Some example. We go with the same example as we had before to see how much difference is in this method. We have a 3R manipulators as we had before, AIs and DIs. What we would like to do is find the screws in a reference frame. As you see here in the recipe, we have 3-part reference frame, target frame, and apply loop closure. We do the same thing here. What we do, say, okay, instead of having this type of difficult version of the system, make it as simple as possible. Make it just some particular position, we call it reference position. Everything 0. Couldn't be anything simpler than that. I put it two times here. I can make it at the same time. I can do 2 type of kinematic analysis. One for the end effector, which we call it Q. We can call it also for the wrist, because for many manipulator we usually use P. We can use both of them, either P or Q. The Q is now of our interest. Let's see. When we put it in this way, in this reference frame, we have a reference frame here, X, Y, and 0. We call it X0, Y0, Z0, or X, Y, Z, because we have only one frame of reference. And we have a moving frame here. We assign a moving frame here as well, and it is much easier to assign the moving frame along the X, Y, and 0. So we have the same U, V, W as well at the end effector. So we have the frame on a reference frame. Now we should find the screws. So if you look at the U0, V0, and W0, this will give you the reference pose that we have for U0, V0, and W0. U0 is along X-axis, V0 is along Y-axis, and W is along Z-axis. Of course, when it moves upward, it will be changing, but at the reference frame, it is quite simple. You know, you can find it by intuition. You don't need any sophisticated manipulation. And also the Q1, what is the position that you find here? Again, very simple. XE would be A1 plus A2 plus A3 along X direction. So it is A1 plus A2 plus A3. There is nothing in Z direction. It is in position frame. Of course, you could use any position frame, but reference frame, but I've put it in a way that it is much simpler. So it is the easiest way is to make everything equal to 0. Now that we have it here, then we go to finding the screws. And finding the screws, instead of having the joint parameters given, or the Denavit-Hartenberg table, we have a table for the screws. And it is very simple, really simple. So we have the same thing here. At the reference pose, we find the screws. You know, where is the rotation of axis here? Of course, this is screw 1, this is screw 2, this is screw 3, all of them perpendicular to the and outward out of the plane. Is it simple as that? So we have these 3 screws, and these have some physical meaning. We are rotating along this. We have pure rotation here along these screws. Of course, if it goes up, we have not only position, we have not only orientation or changing in the terms of rotation, we have also some positions here. Now, so if these 3 are here, what would be the S hat, the direction of the screw 1? direction of all screw 1 is along z-axis, x, y, z, reference z-axis. So all of them are 0, 0, 1. As simple as that. What about the S0, the position vector? S0 was the difference between here to here, as you see. On this screw axis, it is along 0, so there is no S0. But for S2, it is A1, 0, and 1. This is the direction that we get in here. And for S3, as the vector that we get in here, is A1 plus A2. You have a vector that is in this distance, as you see in here. A1, this should be equal to 0. I am really sorry, I should change that. We have only A1 and A1 plus A2. These two should be equal to 0. I will fix that in the slide. So we just get the direction, the difference that this S1 has this vector, has a offset of A0, which is the link length. We had before defined it as a link length, but here we call it the S0 variable. I'm very sorry to have a typo here. So we have A1, 0, 0, and A1 plus A2, 0, 0 here in terms of that. And everything is done now. Finished. Now we go to the target position. The target position is not as simple as this. This has an angle like this, and we can call it, we can have a rotation matrix. Rotation, we call it UVW, a full rotation matrix that we have here. And we have a PX, PY, PZ, a full position vector. Of course, we know that there is no PZ here, but we put it here, and then we will see that it will become equal to 0. This could be for position for P, and for Q we have the same thing. We have instead of having Px, Py, Pz, we have Qx, Qy, Qz. Depending on that, we can have in here. Now, if we go toward the final position, now that we have the reference position and target position find just in 2 minutes, very simple. No hassle to find, the Danavid-Hartenberg problems here, the parameters here. Then we go through the screw transformation. Now we have this screw transformation, as I mentioned here. You should, put this one highlighted in your chapter 2, not in the previous chapter, or just make it this slide 35, highlight this 35. You use this one quite easily. I don't call it T0 to 1. I call it A1, A2, A3, the transformation we got from the screw axis. This is the rotation matrix, and this is the position matrix. And we have S0 and SI and S0 here. Just simply put this one into this equation, and then you can find everything quite easily, find from the angle that we get in here. So we have θ1 in terms of the angle that we can get here. S1 is along S1, we have only θ1. Along S2, we have only θ2. And along S3, we have only θ3. So these three are very, very easily found from this equation. And then you multiply all of them together, you find something like this. This is quite different from the previous version that you see. What is a minus A1 plus A2 here? Something different from what we had before. So as you see here again, we have a rotation matrix and we have the position matrix here, and then we equate them, this one, the final one, to the target position. The target position has a R, UVW, and a Q version. Depending on what you are doing, then we can have it this way. If you use the loop closure for Q, if you have this position vector for Q, the end effector one, we know that Q is equal to the A1, A2, A3, Q0. This is basically vector matrix loop closure. We have a loop closure equation in terms of a vector 1, which is equivalent to just having this tree multiplied by Q0. Here we have Q0, as you see, A1, A2, A3. Look at this point. This is very important. This part is very, very important. And this is the power of the screw representation. A1, A2, A3 times Q0 gives you a general Q. We have theta 1, theta 2, theta 3 on a reference position. Then it will give you a general motion position because of the power of the screw representation. You just multiply this, which is a bit long and difficult, to Q0. Q0 was quite easy. It has only A1, A plus A2 to 0. You multiply this to Q0. This will give you the Q version. The Q version is Qx, Qy, and Qz. You can see that Qx is exactly the same kinematic problem, forward kinematic equation that we have in geometric approach or in the Navier-Hartenberg approach. Q1, Qx, Qy, and Qz is equal to 0. What about the rotation axis? This is equal to the rotation axis. So C theta E is equal to this. C theta 1, 2, 3. You can see this is quite simply seen that the rotations are added to each other because we have the axis, the screw axis are all parallel to each other. So it will provide you theta E is equal to theta 1, 2, 3. Look at this tree equation. We have that before in many slides back, both in the Navier-Hartenberg approach and also in geometric approach that we have before. Very, very easily find this. You go back to the let's say the recipe. The recipe is important. Put it in terms of a base frame, a reference frame. Find all the screws in the reference frame. Then you have a target position. Then you use the axis of screw displacement. In this way, I should add another point that the loop closure is given by this point, that Q is equal to A1, A2, A3 times Q0. P is equal to A1, A2, A3 times P0. If you find this relation to each other, you can get the forward kinematic problem quite easily. So if you just work on this position, if you just have this position, to give a symbolic MATLAB function that you can find the screw axis, it is amazingly simpler to find the position in here. So I will stop here because I would like to give you some more time to think about it. But this one has a proof. The proof of this is a bit hard to give in the introductory book, but the screw axis has the power that we can find any orientation and position just from a reference frame to another target frame by screw representation. I will stop here. I will give again, of course I will fix the slide, we have 2 typos here for the next session, but please work on the screw coordinate, and I will try to make the first assignment somehow related to the screw coordinate. I hope that Reza has given good examples on screw representation that can be worked well with the system. In our approach that we go, we usually use both methods, both the Navier-Hartenberg method the conventional method that has been given in the many books. It is a bit harder, not that much, but a bit harder, with less physical insight. And we go with the screw representation. The screw representation is less familiar with you. You should learn it to get familiar with the screw representation, but it is much simpler. Not here. In the next session, we go in the Jacobians. Becomes much simpler again, and also in the dynamics as we go forward, we use this screw representation to go for the dynamics. Thank you very much for being with me. If there is any question, please, this is time for you to have your questions. Yes?
We have a more complicated robot. How we can find the screw axis using like rotation metrics or whatever?
More complicated than this, a 6 degree of freedom elbow manipulator. Very simple. I will give the example here to you. Since you are doing it in a target position, you can find the screws quite easily. No hassle about D and I and DEI, theta and whatever. No hassle about that. Just look at this. You should practice this. Make it straight, everything straight, and find the screws. Of course, you should have insight. What is the screw? Where is the rotation axis given? But it is very simple to give it in a reference frame. As you see here, it is very hard to give it in here when the screws are twisted here. But when it is just straightforward, you can find it quite easily.
So we just So we just use it in reference frame and nothing.
We just use it in a reference frame and then put this equation from the reference frame to the target frame. And this reference frame has the angle, this theta 1, theta 2s, the reference frames, particular angles are here. The joint angles or the Q parameters comes in here. Yeah, just simple as that. And I don't think it is, you can find any more complex example than that.
So like if we have...
Any example, yeah.
So like if we have two joints that are perpendicular to each other, it seems to me that the first joint change the...
Here they are perpendicular, yeah.
So it changes the screw axis of the next joint, but we just consider...
The reference frame, yeah, in the reference frame, you find them. So they give the direction of them, This gives the arithmetic. It is unbelievable. You cannot believe, because I know that Zahra is familiar with the Navier-Hartenberg. Ali is the same. Ali Hassani, one of your TAs, are quite familiar with the Navier-Hartenberg one. So he cannot leave, the Navier-Hartenberg. But you guys, which are not familiar, leave the Navier-Hartenberg and come to screw. Why? Because the screws, as I mentioned here, put it in a reference frame. It is much easier to find a screw S5 here, which is very difficult to find Z4 here. You see here, just S5 in a reference frame, or S6. This is again perpendicular to these two. We have the perpendicular one. We call it $5, not S5, the $5, the screw here and this screw here, and then you find the screws and the references here, and then you find, we put in the transformation, homogeneous transformation, and everything done. Just as simple as that. Let's think about it a bit, and then we will talk about it later again.
Just can I add one more thing?
Sure.
My issue is that when the robot is moving, then the screw axis of the following links change. So
yes,
it's just very interesting that it doesn't need to consider that.
No, it is. If you are considering that, you are considering that with the theta. When it is changing, A1s are changing, and you're considering that in the loop closure. But you don't have to imagine that. It will done by this loop closure equation. Of course, this needs proof, and it has a very originated proof, very, very, very good proof about that. That we have, rather than the rotation matrices, the Euler angles are very dependent on which one is doing the first one. But here, A1 times A2, A3 times the target reference position gives you the target position. And if you can prove that, you can go for as long as you want. You can have 100 number of joints as we have in a cobra snake that is attacking the prey. We will show it in next chapter.
Thank you.
No other question? Sorry?
سلام صدای من دارید الان؟
علی جان چرا ندارید؟ علی برای از اسکرو تعریف میکنه.
نه اصلا بخشید یه چند تا استاد میاد عقب‌تر من یه موضوعی هست اصلا بپرسم در اون قسمت هایی که دنوی تارتنبرگه
شماره بده به
همینجور یکم مثال رو بیارید همینجور فقط میخوام.
بله مثلا این مثال خوبه. کدوم مثال ساده بیارم.
بکنم صفحه هم یکم دیلی داره الان هنوز تکونی در اسلایدتون نمیبینم. حالا شفایی فعلا میگم موقعی که آره میبینم.
خب
موقعی که ما جدول دنوی تارتنبرگ پر میکنیم خب سوالم اول یکم توضیح میدم بقیه متوجهشن بعد میپرسم. از نظر مکانیکی موقعی که این جدول رو پر میکنیم خب فرض کنید که مثلا من آدم ناشیه مثلا یه سری ربات داره بعد فوقش مثلا یه روزی به این نتیجه میرسه که لینک ها مثلا صدا میده مثلا صدا بعد میاد سر لینک رو مثلا تراش میده یا مثلا سنباله میزنه خب یا مثلا لینک ها توی جوینت های به هم وصله میاد این جوینت ها رو یکم جابجا میکنه در نتیجه میشه که دیگه اون اگه آیکش قبلا 2 بوده الان میشه 195 اگه تتا 1 قبلا اگه آلفا مثلا 0 بوده الان آلفا 0 نیست 2 درجه است 5
کاش که همه ناشی‌ها مثل تو بودن. خوبه
این ترجمه مکانیکی حرفم بود. ترجمه کنترلی حرفم اینه که ما توی این مسئله با یه ساختار نامعین طرفیم. نامعینی از 2 جهت میاد. اول جدول میاد که مثلا الان توی این ربات ما هیچ وقت این ربات تو صفحه نخواهد بود. یعنی موتورایی که هست به جای اینکه 3 تا خط جدول دنوی تارتنبرگ بنویسی در واقعیت 6 تا خطه. یعنی هم یه آفست فاصله آفست موتورها رو باید اضافه کنیم همین که فرضم کنیم جدول همین 3 خط بنویسیم یعنی که طول اون لینک ها رو ما نداریم یعنی اگر هم داشته باشیم تخمین ازش داریم. اینا رو گفتم تا بگم که یه مسئله وجود داره به نام کالیبراسیون سینماتیکی. کالیبراسیون سینماتیکی تا اینجاشو خودم میدونستم بعدشو دیگه نمیدونم که الان من بخوام A1 A2 A3 رو تخمین بزنم مثلا باید چیکار کنم یا اگه آلفا رو بخوام تخمین بزنم چیکار کنم.
یه کمی جلوه ولی اب نداره کالیبراسیون.
یه سوال دومی هم دارم.
اول هم جواب بدم من حواسم پرت میشه بعد سوال دومم بپرس چون همین به اندازه کافی این خودش یه ترم 3 واحدی کار داره کالیبراسیون سینماتیکی و دینامیکی ربات. تو میفهمی من الان چی میگم. فرم ریگرسور رو به دست آوردن سینگولار وایل دیکمپوزیشن و این حرف. سینماتیکی ببین در واقع کاری که باید بکنیم کاری که کنترلی ها میکنن اینجوریه. Let me speak in English because Hussein is also wanted to have. First, what was the question? The question was that when we have a de Navier-Hartenberg problem here as we see, we assume that A1, A2, A3 are given and they are quite precise. But in practice, the parameters of the robot is never known so precise. How should we do that? And as Ali said, there is a topic called kinematic calibration that we can do that. What is the concept of kinematic calibration? I can't go through the detail as I mentioned. It is a long story and a very, very interesting topic of story that we should do it for. If you design and build a robot, you have to do that before going to the control. We usually do measurement. You know, what we do, we say that, okay, assume that A1, A2, A3 is given the nominal points. So if we measure theta 1, measure theta 2, and measure theta 3, we have the kinematic relation. We have this relation. We put the theta 1, theta 2, theta 3, A1, A2, A3, multiply to each other, give a XE2. If I can measure XE, for example, with a camera or something, an external one, not from the joints, but from, suppose that we have a positioning, a Vicon or something that can measure the position here, then it would be much easier to find this. So we have this one, we have this one. They are not the same because the nominal one are not good. We put an error here, this minus this error, these parameters, we put it as a calibration parameters or the unknown parameters, and we use least square method to find them. Find the error, make the error as small as possible. I should add one more thing here, Ali John, for you, just for you. It is very difficult to measure X here, you know that. It's very difficult and very expensive, especially in our labs that we don't have so much expensive. Of course, if you go to the Ilian lab, Bonef, if you can go to the some of my friend lab, you see that they have both very, very expensive camera-based or laser-based laser point measurement unit to find exactly what is the position of the end effector to calibrate this equation. But in my example, we don't have that much money, but we have some talent. We use our talent. How we can use our talent, Ali John?
در واقع سوال دوم اینه که نامعینی ها رو بعدا با روش کنترل
No, not control. Just calibration.
نمیدونم نظر خاصی نه.
You know, with what we do, this would work with the redundant manipulator. You know, it is very hard to say that where is my hand when it is moving in the space. But if I touch someplace, let's say I touched my table. You don't see the table here, but make it fixed point. Put it here fixed. Now move it. If we make it fixed, this fixed point can be measured quite easily. It is very hard to find it when it is in the space, but when it is on the table, it is much easier. Of course, the robot should have some motion, so it should have some redundancy. We call it for redundant robot, and usually Iranian robots are redundant because they are quite clever. They don't never make it non-redundant. Then we move it. You know, the end effector is not moving, but my joints are moving. You know, the arm is redundant. So we call it a self-calibration method. And this can happen not only at the beginning when we build the robot, but after a year or two when the robot is, you know, working, as you mentioned, some parts are becoming, you know, varying, you know, so I'm aging, the length and the angles are changing. You make it another self-calibration and find the parameters of the robot. Of course, again, this is not very good. Your second question is when we have uncertainty, we have a robust control method, which is a very, very interesting issue that we can use there to work for the uncertainty. Our time is finished. Thank you very much. No. تو که سواری میگن یه بنده خدایی یه تاکسی بود طرف دست تکون داد، تاکسی وایساد، تا سینه رفت توی شیشه، گفت آقا شوش میری؟ گفتش تو که دیگه سواری. من چی بگم؟ بگو عزیزم.
سوال دوم اینه که کالیبراسیون سینماتیکی در سوال مربوط میشه فصل 4 و فصل 6. حالا نمیدونم اونجا باید بپرسم یا اینجا بپرسم، اینجا بپرسم بهتره.
تو که سواری ما دیگه شوش بده.
کالیبراسیون سینماتیکی چقدر تو جواب تاثیر میذاره؟ یعنی چقدر تو دقت ربات تاثیر میذاره؟ به عبارت بهتر وقتی ما یه رباتی داریم که میخواد جوش بده، ما ربات رو تو فضای کاری داریم کنترل می‌کنیم. وقتی تو فضای کاری کنترل کنیم ژاکوبیان نامعین میشه. ژاکوبیان خب چیز میشه دیگه. یعنی وقتی تو ربات میخوام تو فضای کاری کنیم چقدر تو جواب تاثیر میذاره با یک گین پی دی. یعنی ما تو ربات داریم، یکی کالیبراسیون سینماتیک کردیم یکی نکردیم. خب یک پی دی یک کنترلر می‌بریم.
جواب تو اینه. The question was how much the kinematic calibration will affect the accuracy of end effector motion. Very much. The simple, don't ask Chandar, so this is not technical. Depends. But, it depends on how much uncertainty you have. But, we don't talk about the accuracy in robotic. We call about repeatability. We don't care about the real accuracy of the robot. We care about repeatability. And that's enough, You can go and search for what is the difference between repeatability and accuracy. تکرار پذیری. به جای صحت از دقت استفاده کنید، accuracy از repeatability استفاده کنید. Thank you very much for
Is there any other?
Yes, after the hours, always it is office hours, but other people.
Yes, thanks.
Thank you very much and bye.